All right, let's take a journey. We're going to the smallest scale you can possibly imagine, deep, deep inside the building blocks of reality itself. We are going to crack the mystery of the atom, and I promise you, what we find, it might just change how you see, well, everything.
So, think about this for a second. That chair you're sitting on, the floor under your feet, your own body. What if I told you all of it is almost entirely empty space? I know, it sounds completely impossible, but it is one of the most fundamental and, frankly, weirdest truths of our universe.
And to understand how that can possibly be true, we need to put on our detective hats. We're going to piece together clues that scientists have been gathering for centuries to finally crack a mystery that started, you guessed it, way back in ancient Greece.
So our story starts, as so many do, with the ancient Greeks. Now back then, most people were convinced that everything was just made of four things: earth, air, fire, and water. But, a few thinkers had a much more radical idea.
A philosopher named Democritus came up with this thought experiment. He said, if you keep cutting something in half over and over again, you'd eventually get to a tiny particle that was atomos, which literally means uncuttable. And then that idea just kind of sat there for over 2,000 years, until a whole series of rapid-fire discoveries completely changed the game.
The first huge breakthrough happened in 1897. Scientists discovered this tiny, negatively charged particle, the electron, which proved that the atom wasn't uncuttable after all, so that opened up a massive question. What in the world did it actually look like in there? The first real guess came with a pretty delicious-sounding name.
It was called the plum pudding model. Its creator, J.J. Thomson, pictured the atom as this solid ball of positive pudding, or maybe dough, and scattered all through it were these little negative electrons, kind of like raisins or plums.
And look, this wasn't just some wild guess. It was based on really good evidence for the time. For one thing, solids are hard to squish, right? So it makes sense that the atoms themselves are solid. And second, think about static electricity. You can rub two things together and transfer a charge. That really suggested that some little piece of the atom, the electron, could be knocked off pretty easily.
For about 10 years, the plum pudding model was the best idea anyone had. But then, a scientist named Ernest Rutherford decided, you know what, I'm going to test this thing. And the experiment he came up with would totally rewrite everything we thought we knew about matter. The setup was actually pretty simple. Rutherford's team fired a stream of tiny positive particles. Think of them like microscopic cannonballs at a sheet of gold foil that was just a few hundred atoms thick. Now, based on the plum pudding model, they totally expected those little cannonballs to just blast right through, maybe getting nudged a tiny bit. But what they saw was just shocking. As Rutherford himself said later, it was like firing a 15-inch cannonball at a piece of tissue paper and having it come right back and hit you. So what did they actually see that was so unbelievable?
They saw three totally distinct and frankly bizarre things. First, most of the particles sailed straight through like nothing was even there. Second, a few of them were deflected at these really wide angles. And third, this was the part that blew their minds, a tiny, tiny fraction of them bounced almost straight back. The plum pudding model had absolutely no way to explain this.
Rutherford realized each observation was a clue. The fact that most particles went straight through could only mean one thing. Those gold atoms had to be mostly empty space. The whole solid pudding idea? It was definitely wrong.
So what about the particles that got deflected? Well, the alpha particles were positive, so they must have been pushed away by something else that was also positive. And that meant the atom's positive charge wasn't spread out like dough. Nope. It had to be packed into one tiny concentrated spot.
And the ones that bounced straight back? That was the final critical clue. For a tiny particle to rebound like that, it must have hit something incredibly dense and heavy head-on. And since it happened so rarely, that dense, positive center, which he named the nucleus, had to be unbelievably small.
And just like that, with those three conclusions, the plum pudding model was shattered, and in its place, the nuclear model of the atom was born, a tiny, dense, positive nucleus at the center, with electrons way out on the outside, separated by a huge expanse of, well, nothing.
Just how huge is that empty space? The nucleus is about 10,000 times smaller than the entire atom. To give you some perspective, if an atom was the size of a giant football stadium, the nucleus would be like a single pea sitting on the 50-yard line.
So later on, scientists figured out this tiny nucleus is made of two types of particles, positive protons and neutral neutrons. Each of them has a relative mass of about 1. The electrons, meanwhile, are way out there. They're negatively charged, and they're so small their mass is practically 0. It's the negative electrons that perfectly balance out the positive protons.
But there was still one question left. Where exactly are the electrons? In 1913, Niels Bohr came along and refined the model. He proposed that electrons don't just fly around randomly. Instead, they orbit the nucleus in these fixed energy levels, or shells, kind of like planets orbiting the sun. And that became the famous model of the atom that we all recognize today.
Okay, now that we have the basic blueprint of an atom, we can start to see what happens when you mess with the recipe. An atom's identity, like whether it's carbon or oxygen, is all about how many protons it has. But what happens if you change the other particles? Well, then you get the atom's alter egos.
It's actually pretty simple. If an atom gains or loses an electron, its overall electrical charge changes, and it becomes what we call an ion. But if an atom has a different number of neutrons, its mass changes, and it becomes an isotope. It's still the exact same element, it just weighs a little more or a little less.
Let's use carbon as an example. Every single carbon atom in the universe has 6 protons. That's what makes it carbon. But some have 6 neutrons, which we call carbon-12. Some have 7 neutrons, that's carbon-13. And a famous one has 8 neutrons, which gives us carbon-14, the one they use for carbon dating ancient artifacts.
All right, let's do a quick pop quiz. Looking at the symbol for carbon-14 right here, can you tell me exactly how many neutrons it has? And the answer is 8. It's just simple subtraction. That top number, 14, is the mass number, protons plus neutrons. The bottom number, 6, is the atomic number. That's just the protons. So you take 14, subtract 6, and you're left with 8 neutrons. Easy, right? So there you have it. We've gone from a solid, uncuttable ball to a miniature solar system that's almost entirely empty space, all held together by these crazy invisible forces. We've solved the mystery of the atom structure. But, solving one mystery just leads to an even bigger question. What kind of power gets unleashed when you finally do the one thing Democritus thought was impossible, and you split the atom?